try to go over some common stuff that pops out a lot, some common themes, and yeah, let's go over the problems, and I guess it will be better to explain what I'm trying to do. So the first problem I want to cover is 2011 G5. Damn it. God. Yeah, I accidentally exited the meet. The first problem I plan to cover is 2011 G5. Give me a minute, I'll share screen. Yeah, is my screen visible?
Yeah, it is.
Okay, so the problem statement reads, triangle ABC is given, and I is the incenter of triangle ABC, and you have like uh, the line AI meets the circumcircle again at D, and the line BI meets the circumcircle again at E, and DE hits AC and AB at F and G, right? And then you have like you draw parallel lines from F to AD and from G parallel to BE, and they meet at P. One second. Yeah, and you have another point you'll define, that is tangents from A to ABC and B to ABC meet at a point K. So these tangent lines meet here. Oops. Uh, this point is K. Second, yeah. So you are asked to prove that the lines AE, BD, and KP are either all parallel or concurrent. So, yeah, they are concurrent in this one. Yeah, so you are asked to prove this concurrency. So give it a try for maybe 5, 7 minutes, and then I'll like you can chip in with ideas if you like, and yeah, then I'll like start hinting towards or presenting the solution.
P is the incenter of CFG.
Yeah, that is a good claim. Just let me check it. Uh, no, that isn't true. That isn't true. Just get the diagram a little more beautiful, maybe by the time you guys are done working on it.
Oh, how was P defined?
I P was defined like you draw a
Okay, okay.
parallel line from F to AD. Okay, yeah. The solution I want to present involves like just angle chasing, so uh, please try to do that if possible. Just angle chase, don't use anything else.
AEFI cyclic.
Yeah, that is true. That's quite easy to get as well. So what he's basically suggesting is these 4 points are cyclic, and that is basically because this angle here, it is equal to this angle, that is a by 2, and that is this as well. So these two angles are equal, and then hence this quad is cyclic. Yeah, that is true. So that is a good point to begin.
Is it then power of point like EA and BD meet at like the radical? Okay, not the radical
Yeah,
center,
that is,
but like you get the
yeah.
point,
So
right?
what you are suggesting, eh, yeah, what you are suggesting is like if you apply radical axes on like these three circles, namely, one second, the red one, the black one, and the blue one, then you would have a concurrency involving AE, BD, and this line, right? So
Yes.
it makes sense to try to prove that K and P lie on this common radical axis of these two circles, then that solves the problem.
Yes.
Yeah, so how do you do that? How do you do that? Once again, I kind of insist on using only angle chasing for this because I want to present an idea which I think is like quite good and using a lot of problems. You can like do a lot of stuff on this problem using other techniques. Like there's like a very short solution using Pascal's twice the price, I guess. But yeah, let's stick to low time.
Using what?
Pascal or Brocard along projective lines. Uh,
Ah, okay.
so does everyone get what the objective is now? We basically we basically translated the concurrency to like read something like we are viewing AE and BD as the radical axes of of a pair of circles for each of them, right? And now we kind of have a line that passes through uh, through the intersection point of AE and BD. That is this line. It is blurred out. Just like increase the magnification of this. This thick line, right? So it's kind of natural that we will try to prove that the points P and K also lie on this line, which they do. You can, if you are on paper, you can either like just guess this claim and or like you can just draw a very good diagram. Also, this is also a kind of important attribute in like solving geo problems where you like think wishfully a lot of time. Like you often need to like guess a lot of stuff which may or may not end up being correct. Any ideas for what we should do next?
Let's a point like T with the second intersection of the circumcircles of C of
Okay.
EFA and DGB, I guess. Yeah,
Okay.
isn't
What
that
do
point
you
on
name
the
the point?
circumcircle of the triangle?
No, it's here. It's what was the point you called? Is it a second intersection of the red and the blue circles? Uh,
I think he means it lies on circumcircle of PFG.
okay, yeah, that is true. That is true. Yeah, that is a part of the solution, so I know the yeah, that is true. Yeah, we will actually use this solution route sort of. So like what we are trying to do is like we want to prove that P and K like pass on a like P and K pass on a line like lie on a line which passes through I. That's basically the radical axis mentioned, right? So uh, a very good approach in trying to prove this kind of situation is like first thing you think of another point which like lies on the line, another nice point sort of about which we know a lot of information, right? And then you try to prove that uh, something like suppose that nice point is x, so you try to prove like px and I are collinear along the radical axis and xi and k are collinear along the radical axis, something like that. In our case that nice point is going to be the second intersection of these two circles, that is I named the point t here. So this is also important to note that sometimes you have a lot of situations, say something like you have a random triangle, uh, or not a triangle. Suppose you have like a random circle and say a random line intersecting the circle, right? And suppose the problem gave you one of the points of intersection. This is kind of difficult to like express, but I hope you get the idea. Suppose you have been like given one of the points of intersection, and this point is like quite nice in the sense it gives you a lot of information to work with, right? Then chances are that the other point of intersection will also give you a lot of information to work with, and it is often nice to introduce in the diagram. Uh, Similarly for circle-circle intersections. So, like if you introduce this point, so now our like strategy is clear. We will try to prove P, T, and I are collinear and T, I, and K are collinear separately. Right. So like before we do this, we will like also note something that is kind of easy. Note that yeah, yeah. Another claim is like triangle CFG is isosceles. Why is that true? Is because like you have something like this angle is equal to this, which is equal to this and this. So yeah, it's a easy angle chase. This basically proves that angle CFG is CFG is isosceles, and it's also like easy to prove that I and I renamed I to H. Oops, I introduced a new point. Also, it is kind of easy to prove that like I and C are reflections over DE. I'll like just leave that to you. It's kind of easy to see that. Uh, so you can also get something like CFIG is a rhombus.
Oh, can you repeat from the reflection part?
Okay, yeah, you can like see for yourself that C and I are reflections about uh, DE.
Okay.
So,
Yeah, fine.
okay, yeah. So now when we introduce the point T, so now we need to basically prove that yeah, first thing, another claim is that which like the point T is nice for a lot of reasons. Someone pointed out that PFTG is cyclic, right? So that is one claim that you can either guess or it's like you can just like sort of like try looking around the configuration and find this. So suppose you have a green line here and a violet line here. So how do you get to this angle? It's kind of hard to at first glance, but one way to do this is like just look at this angle, right? So you're looking at angle FGT and yeah, I deleted it by mistake. Angle FGT is equal to this angle. Oh, actually, no, sorry. It is equal to this angle here, TID, sorry. Right. And similarly, this angle is equal to the other half, that is TIE. And combined, this two angles measure 90 plus half angle A because this entire angle measures this, that is 90 plus half A. So this angle must be 90 plus, this angle must be 90 minus A by 2, right? And also note that angle FPG is basically the angle between the red and the blue lines, right? Here as well. So this is also 90 plus A by 2. So that basically tells you that angle FPGT is cyclic. So this was an important claim, right? And from here, uh, anyone has any questions till now? Okay, so this was an important claim, and from here it's like quite easy to like get to the conclusion that angle F, yeah, from here on you can like prove that angle, sorry, not angle, the points PT and I are collinear. One way to do this is like you just prove something like angle FPT is equal to angle FPI, right? Like which or angle yeah, that is one viable method. Yeah, I'll leave that to you. So the you can like finish off the angle chase from here. And the other side is like you need to prove that uh, Ti and K are collinear. So this part is once again pretty much the same. Using similar methods, you can like prove that angle. Uh, you can like prove TABK are TABK lie on a circle. So these 4 points lie on a circle. It's basically the same kind of like angle chase that you can like do. Basically, yeah, it's easy to see. And like just like in the previous problem, you can again like prove TIKR collinear once you like get this angle chase. Once you get this cyclicity. Uh, any questions? Uh, check the chat maybe. Okay, yeah. If anyone doesn't have any questions, I'll move on to the next problem. Uh, is that all right?
Yes.
Yeah.
Okay, yeah, cool. Okay, the next problem is yeah, okay. Give me a moment. I'll just like draw the state like, problem and then like explain you the statement. Oops. Yeah, this is the problem. Uh, yeah, so you're given an isosceles triangle. No, wait, just 1 second. This is the point of dt. Yeah, so you are given an isosceles triangle ABC, and you take a random point D on the segment AC, right? And then you take a point K on the minor arc CD of circumcircle of BCD, right? And then you extend CD, you extend CK, and let it meet the line parallel to A, uh, parallel through A with BC at T, and let M be the midpoint of dt. So these lines are parallel. Uh, give them the same color maybe. And
Let
you
AB with intersect the circumcircle. I mean the circle at some point E.
okay? Yeah, yeah. Let me just finish telling you the question. And you need to prove angle AKT is equal to angle CAM. Yeah, this was a really bad place to write the statement. Just write it a bit lower. Yeah, you need to prove this holds. Yeah, does everyone get the statement? If anyone has any problem with regards to the statement, please feel free to ask.
Like we have to prove AMAK as original ATC, right?
Come again?
Um, oh, okay, no, never mind. I read it wrong.
Okay. Yeah, let this point be E, because why not?
Then we reflect A over M.
Yeah, okay, yeah, wait a second, I'll do that. Uh, yeah, let's wait a bit for others. So, like, if you notice the problem, then you'll understand that the angles mentioned are like quite weird, right? Like, one of the angles is here, AKT, and the other angle is this CAM. So this. So if you like draw the diagram on paper and like try to do something, then you will find that it's kind of awkward to deal with it, because like in a way the angles are like not sort of in the same place, as in one of the angles is like okay, this is quite vague and stupid, but uh you'll see that like it's quite hard to like relate the angles in any possible way. So what do you do that so that one of the angles become more kind of manageable?
Reflect A over M, and if that point is P, the angle DAM, and of course P and DNE are collinear, and the angle DAM is equal to APT.
That yeah,
And
that is exactly what we are going to do. So what he's suggesting is we reflect A over M to get a point say P, which also means that ADP and ADPT is a parallelogram, right? Because the DT and AP share the same midpoint. So what's the good thing about this is like then these two angles become equal, right? So now you need to prove uh delete this one. So now you need to prove that these two angles are equal. So other words, this translates to proving angle, sorry, not angle, the point AP, uh, P and Q are like, one second. Okay. So this translates to proving AT, P and K are cyclic, right? So as with a lot of problems, what we are, okay, GGP basically gives it away. Uh, as with a lot of problems, what we are basically going to do is like, if you need to prove 4 points are concyclic, often what we do is like we like choose a good fifth point and prove that three of them are concyclic with the fourth, and for the other three as well, right? So if you like you can like prove it easily, like if the circumcircle of AKT hit AD again at some point, then that point is basically just E, because kind of easy to angle chase. Yeah, basically because where's the pen? Because this angle is this angle, and this angle is uh, this. Does it make sense? Okay, I messed up. 1 second.
Shouldn't AEK be AEK be KCB?
One, come again?
Shouldn't angle AEK be KCB?
Yeah, 1 second. Yeah, this angle is
KCB.
PCB, right? Okay. Yeah, messed up. I shouldn't be trying to do this. I need to like incorporate the line CK, right? Because BC is parallel to AT. So what we'll do is like, yeah, so this angle is equal to this angle, which is equal to this angle, right? Uh, Forget about these
Yes.
two for a moment. Yeah, that proves the cyclicity. And this basically tells you that E lies on ATK. Now you need to prove that P lies on that circle as well. So now this is actually really easy. This is because like note that ATPD is a parallelogram. So like this line is parallel to AT, right? Also note that DE is parallel to BC for obvious reasons, which means that the points E, D, and P are collinear, right? And this basically means that ATPE is a isosceles trapezoid, right? Because these segments are also equal. AE is equal to AD, which is equal to PT. So yeah, isosceles trapezoid is cyclic. So that proves the problem statement. Any questions?
No, but the GGB spoils the niceness.
Yeah, I don't think this problem is really about GeoGebra though, because like I think the main point where GeoGebra really helps is getting the point E, like understanding which point you need to work with to prove the concyclicity. But I do think the main point of the problem is the reflection idea, as in you need to tackle the weird angles. So You just kind of shift one of them down by reflecting it, and then it becomes way more manageable. Plus, you get like the entire problem becomes more easily interpretable. Anyone has any questions? Okay, we'll move on to the next problem. And I've lost the statement of the problem. Give me a sec. Okay. Yeah. If anyone has any doubts with the problem, feel free to ask, or I'll just move on. Uh, okay. The next one is from a mock contest on AOPS. Okay, you can't actually get X. Oh God. I'm doing the fake USMO problem from the problem set. If anyone wants to like read the statement. Okay. Yeah, I'm done with the statement anyways. Yeah, so the problem statement reads like ABC is a triangle, right? E is a random point on CA and F is the point on AB such that EF parallel BC. D is a random point on BC, right? And what we are doing is like you draw the circumcircle of ADC and you intersect DF with it, call that point X. Similarly, you draw the circumcircle of ADC, intersect line DE with it, call it Y. Right. And now, suppose the circumcircle of dxy hits BC at a point, say, uh, D dash, then you are asked to prove that D dash and D share this, D dash shares the same midpoint as other words like D dash is the isotopic point of D. Any questions regards to the problem statement?
What has S to do with the problem?
Oh yeah, it is a mistake. Yeah.
Okay.
Yeah, I'm done with the diagram. If anyone has any ideas, feel free to chip in.
Consider the centers of dxy and ABC.
Okay, go on.
It will be O1 and O2. Then we
Okay,
have
go
then we
on.
use power of point, and we get Fy into Fd equals Fa into Fb
Yes.
and Ex times Ed equals Ea times Ec. And we
Okay,
also have that.
I get what you are saying. Yeah, I'll talk about that solution itself. Yeah. I think like centers are not really that important. So I'll just like start by mentioning that there are a lot of solutions for this problem, but I'll like present a, a solution that's like kind of tricky. It's kind of hard to find, but it's the most low tech of them all. For like, you can like check the ops thread for like different possible approaches, but this one is like the most low tech and the most satisfying in a way. Any ideas from anyone else? Okay, yeah, one hint is like start by noticing that you basically have a kind of length condition to work with here because you have got something like, whoops, uh, FA into FB is equal to FX into FB. So what does this statement like tell you about F? Try to interpret this as you are writing the power of F with respect to two circles on two sides. What does this statement mean?
So isn't xy parallel to fe?
That sounds false. That is quite false actually because just wait. Yeah, it's false. What does the length condition tell you about like F? Can we like say F lies on the radical axis of dxy and abc? Does do you get the point?
Yes.
Okay,
Yes.
yeah. So like this was basically the main step of the problem. Like you interpret this length condition in terms of writing like you are thinking of two circles omega 1 and omega 2, and suppose you are writing power of f with respect to omega 1 is equal to power of f with respect to omega 2, right? When you think of this length, when you are like trying to interpret this length condition, this leads to like you can like say f lies on the radical axis of dxy and abc, right? So similarly you can like note that e lies on
Oh,
the
by the
radical
way,
axis of, yes,
I had a doubt.
yeah, go on.
Like, you don't need this length condition to prove f lies on radical axis, right? The radical axis is directly dx, no?
Radical axis is directly.
Dx of these two circles, dxy and abc.
No, no, I'm talking about the, okay, I'm talking about the black circle and the orange circle.
Black circle and which one?
Okay.
Orange.
The orange, yeah.
Ah,
What do you
okay,
call this
fine.
color?
Yeah, yeah, got it.
Uh,
Yeah, got it. Fine.
the main point of the problem is like interpreting the length condition in terms of like powers with respect to circles, right? So this gives you basically that EF is the radical axis of the uh, orangish yellow circle and the black circle. You can just check on GeoGebra as well. You see these points are correlated. So now, what does that tell you? Like, suppose, like, say, O2 was the circumcenter of the orange circle, right? And say O1 was the circumcenter of the black circle. This basically tells you that O1, O2 is perpendicular to EF, right? But think about it. EF is basically parallel to BC, right? And so O1, O2 is basically the line through O1 perpendicular to BC. That's the perpendicular bisector of BC, right? And yeah, that basically proves the problem statement. This is basically what we wanted to prove. Anyone has any questions?
Yeah, got it.
Yeah, anyone else have any questions to ask regarding this? The next problem I'm going to do is RMM 2018 problem 1. Okay, does anyone have any doubts with this problem? I'll delete the picture then. Okay, no, I guess. Uh, yeah, please try RMM 2018 1 from the preset. I'll draw the diagram meanwhile. So the last problem had that really cool idea where you can like interpret length conditions in terms of like power of point. Kind of tricky. Uh, for like an exercise of that, you can like the problems which quickly spring to my mind are like this year's USMO problem 4 had a similar idea. Nice MO from this year, the problem 2 had a similar idea that you interpret a length condition in terms of powers with two circles. Oops. Yeah, yeah, you're asked to prove, yeah, so this is the problem. I'll just explain it. Uh, ABCD is a cyclic quadrilateral, right? And P is a point on AB, and DP intersects AC at point Q. Then you draw a line through P parallel to CD and let it intersect BC at the point K. And you draw a line through Q parallel to BD and let it intersect BC at point L. Then you are asked to prove that circumcircles of BKP and CLQ are uh, tangent to each other at some point. So with a lot of tangency problems, a way to deal with them is like you have to first identify the tangency point. So uh, with GeoGebra, basically this kind of like falls apart. So does anyone have any guesses on what the tangential point might look like?
The intersection
It
of
lies on
PP and the blue circle.
and
Okay, yeah. Like how I initially found out about it was well using like drawing a really good diagram. But yeah, basically I think for this problem at least drawing a really good diagram is quite important to solve the problem because I don't really think there's a lot of good ways to otherwise guess the point. So yeah, so what the first thing about this problem is you have to like guess the point, and the point is basically the intersection of DP with the circumcircle of ABC. Yeah, that is it. So the solution will like proceed in two stages. First, we will prove that E lies on both the circumcircles, and then we will prove that they are tangent. So anyone sees how we can prove like say forget about the red circle for the moment, how we can prove that E lies on the blue circle.
Yeah, so we want to prove that B, K, E, and P lie on the circle. So the angle, we want to show that the angle BEP, which is basically BED, is equal to BKP. And well, BED is equal to BAD, which is
It's a
pi
two line
minus DCB.
angle chase, right? Two line angle chase, right? Yeah. What you are suggesting is true. I want to like just sort of think about it in another way, which is kind of isomorphic to what you said, and that is using beams. I think like understanding how to use reams when you have like circles and parallel lines is quite important, and it like pops up a really awful number of times. So if anyone doesn't know, this is what the Reams theorem states. Suppose you have like two circles, right, and they intersect in like 2 points here, right? Suppose you have a point here, like okay, suppose you draw this. God. Okay, yeah. Suppose you have like two circles intersecting at a point. For example, these circles intersect at the point N and O. And then you take a random point S on this circle, on the left circle, and say intersect Sn with it, right? And suppose the intersection point is say T, and you take a point say uh, U on the left circle, and you intersect it with and you intersect it with O, and suppose UO intersects the right circle once again at a point V, right? So then you have like just like blur the other point so that it becomes easier to see. Yeah, and then basically you have like SU is parallel to TV. And this is basically angle change. One second. Yeah, this becomes much more clearer. What you do is basically, excuse me, this is if this is theta, then this is theta, and this is then pi minus theta. Yeah, so this is called Reams theorem, the fact that SU and TV are parallel to each other, right? So this often comes up like while solving problems which involve circles and parallel lines. So this is like a good intuition to always keep in mind. Like look for Reams whenever you have circles and parallel lines. So like think about it. So look at the blue circle and the black circle, right? Or also note that converse of dreams work all the time, right? Like suppose like the blue circle and the black circle intersected at a point E dash, right? Suppose E was E dash for the time being, right? And suppose you extended KB to, and now note that if you, now K is a point in the blue circle, right? If you extend BK and it hits the black circle once again at C, right? And then suppose, one second. Yeah, and suppose now you uh, produce the line EP, right? And it hits the black circle one. God, wait, I messed up kind of. No, not. You actually don't do it with phantom points. You can just like argue that since like E lies on the black circle and you have like if you produce EP and it hits again at D, right? You have since you have PK parallel to CD, right? The main point to note is like uh, A, B, and C are collinear, and E, P, and D are collinear. So you can just like conclude that E lies on the blue circle. Is the logic clear? Do you get the argument?
Yes.
Okay, if anyone has any doubts, please ask. Right. Okay. So this basically tells you that E is on, and similarly, you can prove uh, that second. You can prove that it lies in the red circle as well, which I had just like blurred out. So now, oh, okay, yeah. So now note that we no longer need the points K and L, right? We are just like we just want to prove that circumcircles of BP, E, and CQ, E are tangent to each other, right? You can just like delete the point K and L, like they don't exist. Uh, yeah, yeah, they don't exist now. Yeah, so there are like a lot of approaches for this. Uh, One way to do is like you just like introduce the centers and just like forcefully angle case kind of. Suppose this circumcenter of this is like OB, uh, OC. You need to prove that EOB and OC are like uh, collinear, right? So one way to do it is like nothing special here. Like you can just prove this part in a million ways. So something like the angle OBEP is basically 90 minus angle EBP, and note that angle EBP is basically angle EBA, right, which is equal to angle ECA, which is equal to angle ECQ. There is 90 minus angle ECQ, which is equal to angle OCEQ. Now, since EP and Q are collinear, this means that OB, OC, and E are collinear. Yeah, and that finishes the problem. Yeah. Any questions?
Oh, how did 90 minus ECQ give
Oh,
OCEQ?
yeah, because like suppose you have a triangle like F and O. Okay, okay. Like suppose you have a triangle like this, right? Then suppose in this triangle N is the circumcenter, right? So if this angle is A, right, then this angle is 2A and this are equal. So this is 90
Okay,
minus
fine.
A, right?
Yeah.
This is basically what I'm doing.
Yeah, fine. Okay.
Yeah,
Also,
any
like
other questions?
I don't have a doubt in this problem, but like related to this theme, like when two circles like
Yeah.
have one point in common, how to show that they are tangent? Like, can you cite some two or three more ways? Because like this is the most.
Okay, yeah. So like uh in most ways, like a very good approach is the first thing getting the point right. So that is quite important most of the time. Another approach is like where what you can do is like you take a tangent, say uh you consider the tangent to the blue circle and prove that it is also tangent to the red circle using like angle chasing repeatedly. That is
Okay,
another technique.
I see. Yeah. Is there like any other way to prove them tangent? Like after you have guessed the point, or like the tangent one is the only. Like take tangent to one circle and prove it is tangent.
Homothety.
Not
Ah, okay.
really. I don't Quantity is one, but it doesn't come up that often. Maybe uh, another way is, yeah, I think the common tangent approach is the most viable one. Again, like if you have something like this, where you have like if you have some a situation where you have like chords to work with, right? So like suppose you have these are two tangent circles, right? And you have like sort of chords to work with at the tangency point, right? Then suppose the point of tangency was A and you have like chords A, B, and AC. Of so the tangency is equivalent to proving angle BAC equals to angle the arc subtended by AB by 2 plus uh, the arc subtended by AC by 2. In other words, that this angle is the sum of this and this. Yeah, this is another way. But other ways, like you can like find the point common on apart from. Oh, sorry. Yeah, I already mentioned that. Yeah, it's basically these and not a lot of freedom you have. Yeah. Any other questions? Okay, I'll move on to the next problem. Then, if anyone has any questions, please. Okay, then I'll like move on to the next problem. Next problem is Russia 2021 10.8. Actually, give me a minute to draw this because it is hard to draw. Uh, Please read the problem meanwhile while I try to draw because drawing this can actually take a while. What happened to our
Which ARMO are we discussing right now?
2021 10.8? This is the only one left in the set.
Okay. Oh, there is 2018 9.8 also, by the way.
Oops, yeah, that is the next problem. Sorry. Yeah, it's the 2021 problem. Okay.
Haven't you messed up the order of A, B, C, D, E?
Oh, I forgot to name the. Okay, I'll just do it. Not a big deal, I guess. Yeah,
Uh,
it's good now.
yeah.
This was like. So I like explain the problem statement. Yeah. So yeah. Give me 1 second. Uh, yeah. So the problem statement is like you have a triangle AXY, right? And there is a circle that passes through A, and suppose it hits AX at B, XY at C and D, and YA at E, right? And also suppose A dash is the reflection of AWRT XY. Right. Now suppose XE hits the black circle, which is the one going through A at point Q, and suppose YB hits the circle at point R, right? And these two lines, the blue and the green lines intersect at P, right? Then you draw the circumcircle of PQR, right? Like the circle, and you also draw the circumcircle M8, right? And suppose these two intersect at points and N. And then you are asked to prove that CM and DN intersect at a point on PQR on the red circle. Is the problem statement clear to everyone? It
Yeah.
intersects here at a point. Let's call it Z for now because XYZ. Yeah. Yeah. Anyone has any ideas to start the problem with?
CDPZ cyclic.
CDPC.
CDPZ. Yeah.
Okay. Is it though? No.
Oh, sad.
What can you say about the point Z? Again, this problem, a good diagram is really important to solve the problem.
Isn't
Oh, is it
XZY like tangent to MZN?
ZY tangent to MZN.
Tangents to,
That is
yes.
no, it's like it would be unsymmetric first of all, right? Okay. You're saying ZY is tangent to what circle?
The circumcircle of XZY is tangent to the circumcircle of MZN.
XZY and MZN. Okay. Oh, that was a okay. Let's see. No, it's not. It actually intersects somewhere.
It intersects at P.
Does it? No.
Oh,
Oh, can you draw BD ones?
BD. Okay.
Okay, the
No,
Z
it's
is not
not
possible.
collinear with the if you that's what you were thinking. It also would be kind of asymmetric, right?
Oh, does Z lie on A dash? Oh no,
Z lie
possible.
on
Never
what?
mind. Whatever. Oh no, it's not possible. Never mind.
Okay, so like the last problem had an idea where we like okay, yeah, we are not at there yet. So like can you tell me something that you can spot from the diagram about Z, something that looks to be true, you think is true about Z? The problem is really about understanding Z, M, and N because those are the points you don't have a like ready-made grip on sort of. So what can you say about Z from just like looking at the diagram drawn on the GeoGebra?
PZ is angle bisector of BPX. Sounds vague though.
BP what? BPX.
PZ is angle bisector of BPX. It sounds
That's
vague
probably
actually.
false. No, yeah, no, it's not.
BZP is cyclic.
No, please come again.
Is BZPE cyclic?
BZPE. One second. No.
MNPZ cyclic.
One second. MNPZ. Yeah, that's by definition, right? Or
Oh,
like that's what you needed to
yes.
prove.
I didn't see that. Think so.
Okay, what like what's special about Z on the red circle? Think of it like that. I don't know how else to like think at it. Like CM and DN intersect at a point Z on PQR. That's what you are asked to prove. What are some properties of Z with respect to the red circle?
Can we show that Z is the uh,
Yeah.
ZQX and ZRY are similar?
Uh, can you mention once again?
Isn't it like the Mikkel's ZQX and ZRY?
Yeah. Yeah. Okay.
Aren't they similar?
Okay. That is a bold claim. One second.
That would imply like Z is Mikhailov, like XQRY, which is not true because we checked XYPZ not cyclic.
Okay. Yeah, that was like a bold claim. I'll go with what Atul said.
Uh, is CQXM cyclic?
Once again, C what? Once
Uh,
again, can you mention the points?
I think
I should like
I
write them
think
down.
that looks like a Q. So it's CQXM.
Yeah, it is cyclic. Yeah, that is true.
Okay.
Yeah, he actually got an observation right. Something else. I was actually going to arrive at this from something I wanted you guys to see about Z. That's how I found it basically. But yeah, observation is observation. So okay, since someone actually noticed, let's do it that way. So suppose CQXM was cyclic, right? So what does that tell you about M? What other definition of M do you get? Forget about the violet circle for a while. Violet circle is useless. What does that tell you about M? Okay, you can just define M as the intersection of the gray circle and the blues and the red circle, right? We are using phantom points, like alternate definitions, basically. You can always use alternate definitions if you have the chance. Anyone? understands or doesn't understand.
Yeah, yeah. Hmm.
Okay, so uh, okay, so again, think about it. So suppose you stumbled upon the observation that M also lies on CQX, right? So now think about this. Think about the gray circle and the blue circle. Sorry, and the red circle, right? So you have again like think about it. You have like the points X, Q, and P connected, and by definition, Z lies on MC, right? So what does that tell you? Q and C were the common points, by the way. So wait, actually, no, actually, never mind. We sorry, I was uh, wait, what went wrong?
Therefore, PZ is parallel to XY.
PZ is parallel to XY. Yes, yeah, that is the observation I was actually talking about for a while. I messed up, but yeah, got the right. So basically, note that if you are looking at the red circle and the gray circle, right, what are the common points of intersection? Q and M, right? Now you note that X is a point on the gray circle and XQP is like uh, connected, and also note that MCZ is also sort of connected, right? So by Rieman's theorem, you get that PZ is parallel to CX, which is basically XY. So does everyone get this part? Does everyone get this part? What I'm suggesting is
Yeah.
CZ is equal to is parallel to Y and CQXN is cyclic. Yeah, this is interesting. That's what we did. Just P not P. Okay, so how I did the problem was like I first figured out PZ is parallel to XY by drawing a good diagram, right? And then basically I sort of thought about rings in the like a reverse version, sort of like if you have like MCZ and XQZ are sorry XQP are collinear, so that means that Q and M must be the intersection points of two circles, and you have the red one and you introduce the gray one, sort of. Right. So that is how I thought about it. But yeah, you can just do the other way as well. So now think about it. We have like alternate definitions for both Z, M, and N. Right. So what we can do is like we can so like the violet circle that I kind of like just did it, right, was kind of difficult to deal with because A dash was like kind of hard to deal with given it was like kind of isolated from the other points, and we are like interested in dealing with the points which are more like sort of close to PQ and R, right? So one way to deal with the problem is like you define M to be yeah, you define M to be the intersection of circumcircle of CQX and the red circle that is PQR, and similarly for N, right? And then and you also define Z to be the point on PQR, that is the red circle, such that PZ is parallel to XY, right? So we are using redefinitions basically everywhere. And then you can easily prove by Reams, which we just discussed, that with that definition, Z, P, and M are collinear and Z, D, and N are collinear, right? So what remains is that you need to prove that M and N lie on the violet circle, right? So how do you do that? So you basically we will prove that
We
N
can just
lies on
do
the
X
violet
and
circle.
Y is equal to.
Okay, yeah, tell me. X and Y
We
is
just want
equal to
XMY is equal to angle A, but XMY is XMQ plus QMY. XMQ is
one second.
XCQ and
Okay, can you just repeat X and Y equals to? Go on.
oh, XNY, yeah, XNP plus PNY.
X and P plus P and Y. Okay, you'd probably get stuck with this at some stage, but okay, let's go on.
And we write Y and P as, I mean, what is that? R, okay. What? Okay, can we just do it with XMY? It's easier. I can't make out the point
Yeah,
labels.
how do you calculate and this is the point here. This is R, this is D, Y. Do you get the point labels now?
Yeah, okay.
Oh God. Okay, yeah. What were you suggesting about this to be?
MCDN isn't MCDN cyclic. Must
NC. Once again. One second. NC. Can you like repeat the 4 points?
MCDN.
MCDN. Okay. MC. Where is D? No, it's not. It's not.
Yeah, sorry.
Okay, think about it. You introduce the gray circle, right? The gray circle tells you a bit about angle Y and D, right? So you need to prove that angle X and Y is equal to angle A, but you only know about angle Y and D, and it's also plus X and D. You don't know about X and D. How do you figure out X and D? That's the point of the problem now. How do you figure out X and D? Let's think. Let's actually do the other side of the angle case and let's see where that gets us, right? Sort of, if that makes sense, right? So now note that you want to prove that angle X and Y is equal to angle A. So angle A can be, angle A is basically this one right here. Okay, so note that angle Y and D is equal to, where did you go? Angle Y and, okay, I just zoom in, right? So this angle is equal to this, right? Angle BRD. B was somewhere to the left, right? So, and BRD is basically angle BAD, right? So the left. So if you are writing it like angle X and Y equals to angle Y and D plus X and D, Y and D basically translates to BAD, right? And so you want X and D to be equal to where do we? Yeah, we want that to be equal to angle EAD, right? So what do we get from there? Where does that take us? Try to like backtrack a concept with, or something else to work with. We want X and D equals to EAD. Now notice that there are more points on the circle. So EAD can basically mean E, like any other point on the circumcircle which is good D equals to X and D, if you get what I mean. Like you can write any good points for A, right? I'll just write it as PD by 2, RPD by 2 to prove. Okay. Any ideas?
How did you write X and D to be in ED by 2?
Yeah, we will prove that. That's what we need to prove.
Ah. And why do you need to prove that? I didn't get it.
Okay, so you want to prove that angle X and Y is equal to angle A, right?
Yeah.
So note that you have a gray circle to the right that is circumcircle of YR. Okay, the circumcircle of YRDN, right? So you break the X and Y as Y and D plus X and D, right? Now
Yes.
try to angle chase with, sorry, you try to angle chase with the Y and D part. Where does that get you? Y and D is equal to BRD, right? BRD is basically BAD. True.
Don't we
So, and
want X
you
and
want
D
to
equal to arc DE, not by 2?
arc D. For me, I use arc D as angle EOD, where O is the circumcenter. So,
Oh, okay.
so arc ED by 2 for me means EAD. Yeah.
Yeah, got it.
Okay, now fine.
So we want XQDN cyclic.
Yeah, yes, that is true. One way to get, he basically suggested that XQDN is cyclic. One way to get there is like, notice that we wanted to prove X and D is equal to EAD, right? Note that EAD is also equal to EQD, right? I'll just do this like this. And you also have, and you want to prove that angle X and D. So you want to prove that this angle is equal to this angle. Other words, you need to prove that angle, sorry, the 4 points X, Q, D, N are cyclic. If you like just draw it around them, you want to prove that this orange circle exists or this yellow circle exists and it passes through X, Q, D, N. Does everyone get the thing? How we arrived at it? So you prove that this circle exists, the problem is over. So how do we do that? It's basically angle chasing, I think. What angle do we work with? Uh, oh yeah. So note that you have like, yeah, you have a gray circle and a blue red circle here, which involves the point Q N, right? And X is on the gray circle. So it makes sense to like work around the chords involving these points, right? So you get something like angle Q and D, yeah, is equal to angle, uh, 1 second. Okay, yeah, okay. I think okay, yeah, sorry. For this one, we'll be dealing with the other side. Sorry. Yeah, so you have like angle Q and D, right? That is equal to angle, uh, okay, I messed the angle here. Okay, yeah, sorry, yeah, yeah. I got it right. Okay, so you have like you have like angle Q and D, just like delete the mess here. Okay, like you have this here angle Q and D. So this angle is equal to this angle, uh, is equal to angle Q and D is basically angle Q N Z, right? And this is equal to angle QMZ, that is basically angle QMC. So this here, this is equal to angle uh, QXC or QXD. So yeah, so you have like these like angles are the same. So yeah, so you prove that the yellow cyclicity is true. Yeah, that finishes the problem. Does everyone get the angle case?
I didn't get the final angle.
Okay, I'll just write it out, I guess. You have angle Q and D, right? Q and D is basically Q and QMZ is basically angle QMC. Sorry, QMZ. Yeah, QMZ is QMC. Right, and now you are in the gray circle, left gray circle area, right? And QMC is
Yeah, got it.
QXC, and QXC is QXD. Yeah, anyone has any questions? Anyone has any questions? Or I'll move to the next problem. This was a hard problem. This is probably the hardest problem in the entire set. So feel free to ask if you like missed out on the motivation on any of the steps.
What do you do like if in a diagram many things look true but like they're not?
Draw a
Like
good time.
despite even a good diagram, like this was GGB but like XYPZ looks cyclic. And it almost is.
think like doing degenerate cases might be good if you are trying to prove something like uh say something like if C was equal to D, would the claim still hold true? Or if something like if your claim is looking antisymmetric, that would probably be false and something like that. So kind of that is sometimes the point, like you have to make the right claims. For me, like I started off the problem by it took me a while, but once you get the Z definition right, that is like PZ is parallel to XY, right? It's like gives you a good foothold on the problem. Someone else like started the problem with the left side cyclicity, left gray cyclicity, right? And then you can again backtrack. So yeah, noticing one of them was the key for this one. I think eyeballing is like you just need a lot of practice, I guess.
Yeah, thanks.
Okay,
What would you do if the diagram doesn't fit on the paper?
why would this not fit on the paper? This would fit easily, right?
It's
Just draw the
huge, right?
diagram smartly. Just draw angle like kx small,
Sure.
like yeah, that's up to you. I think I'll use Jamboard for the next problem. Kind of hard to like do it. If anyone has any questions regarding, I'll move to Jamboard. Actually, move to Jamboard, so but you can still ask. Okay, yeah. Where is the problem? Yeah, it's the last in this set that is 20, Russia 2018 10.7 and 9.8. The same problem. Yeah, let me draw the. Uh, okay. Yeah. So the problem states that ABCD is a quadrilateral such that angle BAD is equal to angle BCD. Right. Now M and N are points on AB and BC such that MN is parallel to AD and MN is equal to 2AD. K is the middle point of MN, right? And uh, H is the orthocenter of ABC. You are asked to prove HK parallel CD. This is what you need to prove. Okay. Yeah. Any
Oh,
ideas?
I'm not sure if this works, but maybe extend ND to meet AB at some point T, and then somehow use the
ND to
midpoint
meet
theorem.
AB. Okay. What are you suggesting? Like, okay.
Like just ND, ND, not CD.
Oh, yeah, this is same line. Yeah.
Yeah, and now just use the midpoint theorem somehow. Not sure if this works.
What What does that tell you? What does the midpoint theorem give you? Yeah, it's
Not
not
sure.
that.
Like it would just give that reflection of M over A and N over D.
M over what?
Over A and N over D.
Yes. Go. Okay, yeah, they are the same, right? Okay, I get what you mean.
Yeah.
But that's like not that like consequential, I think. Also, like the midpoint theorem would be quite useful if you are like not dealing with K, I think. But K is given, K gives you a lot of freedom, I think. K is quite good.
MKD is a parallelogram.
Yeah, that is really true because this and this
So
sort
K and
of
CD
relation.
cyclic.
KNCD cyclic, right? Yeah, this was the starting step of the problem, and yeah, what's next? Okay, what if HK was actually parallel to CD? What would that actually tell you? Like,
If it was
yeah,
parallel or
so
perpendicular.
perpendicular, sorry, yeah, sorry, yeah. If what if HK was actually perpendicular to CD? You suppose this was true, right? The red statement was true. You also know that this is true, right? Uh, CH is perpendicular to AB, at AB is basically KD, right? In other words, CH would be perpendicular to KD. What would these two statements mean? The this
H
and
is the
this.
orthocenter of KDC also.
Yeah, exactly. Yeah. So these two statements would mean that H is orthocenter of CK as well. Yeah. So you again have like two alternate definitions for H. You could define H as the orthocenter of ABC. You could also think of it as orthocenter of CDK. Right. So once again, we will kind of use a phantom point approach. What we will do is like we will assume H is the orthocenter of CDK, and we will prove that it is the orthocenter of ABC. Right. So do you get what I'm trying to do? This is a really classic phantom point approach. Right. Also, like, note that because of this thing, because CI is perpendicular to KD by the new definition, it's also perpendicular to AB. So you either need to prove that VH is perpendicular to AC, or you need to prove that AH is perpendicular to BC. Right. Now, which one makes more sense? The line AC isn't even really drawn in the diagram yet. I think we should like try to prove AH is perpendicular to BC because it just kind of makes way more sense in a way. So what else can you do with the configuration? Can you like think of any more like one thing we have used in the problem so far is like if a line is perpendicular to some other line, suppose if a line L1 is perpendicular to a line L2, then it is also perpendicular to any line parallel to L2, right? So can you like think of using that repeatedly to get something? Or a better way, how can you introduce more lines perpendicular to BC?
Do we get DK parallel to AH somehow?
PK
Like
parallel to
then D,
AH.
not sure. Like it is parallel, then we prove DK perpendicular to BC.
PK perpendicular to it. 1 second, let me check. Yeah, DK perpendicular to BC is probably false because DK is perpendicular to CH, right? And CH and BC are not the same line.
Ah yes, right.
Any ideas? Okay, I'll give you a hint. Try to incorporate the antipode of C in this circle. So this is the point, C dash. Yeah, try to work with this. What does this give you? Okay, so what I did was I introduced the antipode of C in the red
So
circle,
C
right?
dash K parallel to AH.
C dash K parallel to what?
AH.
No.
Wait, what is? Yeah, okay.
But like just
I'm reading again.
take a look at this, right? Because like
Yeah,
you
I'm
know
reading
that this is a
angles
right
now.
angle, right? And also you have like CK is perpendicular to HD. This basically tells you that HD is perpendicular to KC dash, right? What else? You also know that HK is perpendicular to CD, and also this angle is 90,
Parallelogram.
right? Doesn't look, yeah. So this means that AKD dash, sorry, AKC dash D is a parallelogram, right? What else do you know? What else can you say? We are moving closer to like the idea that I like talked about a while ago, that if you have like a line is perpendicular to another one, then it's perpendicular to all lines parallel to it. How do you use that? It's hard to motivate, it's kind of spontaneous from here, but yeah, I'm thinking of a way to motivate it. Okay, also note that Mn was equal to 2AD, right? So these lines are also equal. These segments are also equal. Doesn't look equal, but it is equal. So Kn is also equal to AD, and they are also parallel. What does that mean? I'll just write it.
AK is
AD is
parallel to
parallel to
ND.
Kn. Yeah, basically this is a parallelogram, right?
Yeah.
So what we did was like AD is equal to Kn, and also AD is parallel to Kn, which means that AKND is a parallelogram. Right. Now look at the thing, like you have a red parallelogram and a blue parallelogram, right? So this means that suppose the common center of the parallelograms is the midpoint of KD, right? Suppose that point was O, I'm not naming it, right? So you have like HO equals to OC dash and AO equals to ON dash, right? So like you can easily prove that this is basically a quadrilateral in which the diagonals get bisected. So you can like easily prove that AHNC dash is also a parallelogram, right?
Yeah.
So yeah, what does that give you?
Yes.
So AH is parallel to CC dash.
And CC dash
Okay, I mean
is
C dash N.
Yes.
and C dash is perpendicular to NC. So and NC is basically BC. So yeah, that was the problem. Yeah, so this green parallelogram exists, and this means that uh, AH is parallel to NC dash, and this means that AH is perpendicular to PN, which is BC. Does anyone have any questions? This was actually a really nice problem. It is not that hard, but the solution is really satisfying. If you actually go on your like, you'll find a lot of people have used like all sorts of projective heavy machinery on this. But yeah, the uh, most natural solution is like really smooth. Any questions regarding this?
Can you please tell again how HK dash D is a parallelogram?
HKC dash D. Okay. Okay. Do you agree that HK is perpendicular to CD by definition? Right.
Yes.
And C dash is also 90 degree. In other words, C dash D is also perpendicular to CD.
Yes.
So HK is parallel to DC dash.
Yeah.
Similarly, like HD is HD is perpendicular to CK
Okay,
by
yeah, got that.
definition.
Yeah, yeah, fine.
Okay.
Hello. The meeting was actually supposed to end at 8:30, so maybe you should try to wrap things up.
Yeah, this was the last problem. I am done basically. So if anyone has any questions, they can just ask. Yeah, from my side, it's over. So I don't have anything else to cover. Any more questions from y'all, or I can just like end the meeting right now? Okay, yeah, I think I'll end it here if no one has any more questions.